couple definitions. If we are talking about one-to-one functions, first of all, if something is a function, what does that mean?
It's continuous and the domain doesn't repeat. No.
Okay, it doesn't have to be continuous, but
Domain.
the domain doesn't repeat. That is correct. So if it's a function, we know the x never repeats. If it is one-to-one, then the actual definition says two different inputs in the domain correspond to two different outputs in the range. What that's saying is if you put in two different x's, you're going to get out two different y's. In other words, y will never repeat. So function is x doesn't repeat, one-to-one is y doesn't repeat. So in other words, that's the little blurb down here. If you have two different x's, they have to give you different y's. So if we looked at some different representations of functions, this one is a mapping. So if I looked at that mapping, the first box represents my input or my domain. The second one is my output or my range. First of all, is that a function?
Yes.
Yes. How do you know it's a function?
Because the domain doesn't repeat.
All those x values are different. We didn't repeat any of them. Second question, is it one-to-one?
No.
No, because if I look at this, my y's, 38 repeats. So you can write it out in words, or I usually do just a 1-1. And my reason is the 38 repeats. We get the same y value with two different x's. B. This is looking at a set of ordered pairs. So if I'm looking at this, is that one one-to-one? Yes. You look at all your y values, they are all different. So that one is one-to-one. In terms of looking at a function, there's a couple different ways we can decide if something is one-to-one. So the first way is an algebraic approach. So if things are one-to-one, we have to show if the y values are the same, then the x had to be the same to start with. So if I asked you if this was one-to-one, the algebraic approach is if f of a equals f of b. So if two y's are equal, then a had to equal b. Then they had to be the same x value to start with. Is this one not on your handout?
It is, it's just all the way down here, out of order.
Oh, what did I put? Okay. So you look down. Yeah, I put another slide on there before. So the algebraic approach would be f of a equals f of b. So if I plug in an a, you get negative 3a plus 7 equals f of b. If I plug in a b, negative 3b plus 7. If I'm trying to solve this for, let's say I want to get a by itself, what would you do?
Subtract the 7 divided by -3.
So if I subtract my 7, divide by negative b, or negative 3, I get a equals b. So what does that mean?
1-1.
It's one-to-one. I figured out that the only way those y values could be equal was if I had the same x to start with. So that's the algebraic approach to say, yes, this is one-to-one. If I look at this one, if I did the f of a equals f of b, f of a equals f of b, what would you do to solve for a?
Square it.
Yeah, we need to get it out of the square root, so we square each side. So then if I'm solving for A, what would we do?
If it's all flat.
Hmm?
Which one is on the left?
Let's say I want to get A by itself.
Subtract 49
Mm-hmm.
and then divide by negative. No, then you take this.
Okay. If you add an even root, what do you have to put with it? So I get A equals plus or minus B. So that tells me if my Y values are the same, they could have been the same X to start with, or they could be opposites. I could put in like positive 7 and negative 7 and get the same thing. So is that 1 to 1? No. Because I did not get just A equals B. I got A to equal positive or negative B. Now, the algebraic approach, some people are fine with it, some people really dislike it. The other option we have is to look at a graph. When we're looking at a graph and trying to decide if something is a function, what do we do?
Horizontal line test.
Well, to check for a function, we do vertical line tests. So to check for 1 to 1, we do a horizontal line test. So if the graph, every horizontal line hits it in at most one point, then it is 1 to 1. So if you are looking at a function, if it's 1 to 1, I should be able to draw horizontal lines that never hit it more than once. Is this one going to be 1 to 1?
No.
Kind of. It's hard to tell. That was probably not my best drawing, huh? What if I redid it and did it like this? Is this 1 to 1? No, because I can see we have a horizontal line that hits it multiple times. But if I did that, would that be 1 to 1?
Yes.
So let's go back to the two examples we just did. You could grab your graphing calculator and take a look. So graph. F of x is like our y. So you go to your equation, equals negative 3x plus 7. So graph that, tell me what you see. So what's the graph?
Short line.
It's a straight line. So is that 1 to 1?
Yeah.
Yes. So we can tell from our graph. We got something like this. That's 1 to 1. All right, if you graph this one, the square root of 49 minus x squared. No. When you look at that graph, it's like a semicircle.
Cool.
So we can see that one is definitely not 1 to 1. It fails the horizontal line test. You can draw a horizontal line that hits it multiple times. So we can determine 1 to 1 by looking at the equation or looking at the graph. Things that will typically make it not 1 to 1, when you have a square, because if you're solving it, you get plus and minus. Absolute values, think about our parent functions. X squared was a parabola, that's not 1 to 1. Absolute values are not 1 to 1. Even polynomials, when we start having multiple zeros, there's a high probability that it will turn out to not be 1 to 1 in the end. Right. Any questions about that? So you guys do those two for me. Take a second, sketch a rough graph. So what's x squared? We should know that one without our calculator. It's a parabola, so it is not 1 to 1. What about x cubed? Yes, that's our chair. So that one is 1 to 1. Passes the horizontal test. All right. So the reason we're talking about one-to-one is if a function is one-to-one, we can find the inverse. An inverse is like the opposite. So to find it, what we do is essentially just flip the x and y values. So inverses, we flip x and y. If it's not one-to-one, what's wrong? Oh. If it's not one-to-one, that means y gets repeated, and so once you flip it, your x's are repeated, and it wouldn't be a function. So that's why we're specifically looking at one-to-one, so that the inverse is also a function. The symbol for inverse is f to the negative 1. So that is not the same thing as a negative 1 exponent, it's just telling us the inverse of a function. So if I ask you to find the inverse of this function, what would we do? Oh, hold on. That's not good. I don't know why this is different than yours. Let's see that. I have one more point on yours, don't I? 327. Sorry. So, what do we do to find our inverse?
Change the signs.
Nope. What's the inverse say? Nope. Go back.
Reverse
Yeah.
the x and y values.
Reverse the x and y. So what would the first order pair in the inverse be? Negative 27, negative 3. Negative 8, negative 2. Negative 1, negative 1. 0, 0. 1, 1. 8, 2. 27, 3. You guys do B. Flipping the points. So what are the points in the inverse? Mhm.
1,
Negative 1.
Alright. So if you notice, the domain of the original function, the x's in the original become the y. So the domain of the original is the range of the inverse. The other thing that we need to note, inverses are opposites of one another. So if you do both operations, they should cancel each other out. So if you have, like, for instance, a cube root and a cube, they're opposites of one another. So if you have the cube root of x and you cube that, you're left with x. If you have x to the third and you do the cube root, you get x. So inverses are opposites, they cancel one another and will give you back just the original x. So let's say, oops, that's not the first example I have for you guys. All right, if I want to decide if these are inverses. Okay, so I'm asking you to verify that these are inverses. I just told you that they were, that was the example I used, but if we want to do it, all we're doing is a composition. So you have to take one and plug it into the other. So we would have g of, you start on the inside, g inverse was, so then we take that and we're plugging it into g. So g is whatever we put in to the third. So if you do the cube root of x to the third, you get x. It is not enough to show one of these. We actually have to do both ways because it is possible for one to equal x and the other not. So I just need to do the composition in reverse. So g inverse of g of x. So you start on the inside. G of x was x cubed. Putting that into the inverse. So we have the cube root of x cubed. And the cube root and the cube, again, cancel and we get x. So if you do both and you get x both times, then you can say they're inverses. If you do one of them and it's not equal to x, then there is no need to check the other one. That's all you need to say that they are not inverses. So now we're going to practice a few of these. So I want to decide if these are inverses of one another. So what we're going to have to do is put one into the other. So if I ask you to do f of g of x, g of x is the inside. There is my g. So if I put that into f, okay, function f is 2 times whatever I put in plus 3. And the thing I'm putting in is my 1/2 times x plus 3. So 2 times 1/2, those cancel. So we get x plus 3 plus 3, which is x plus 6. What does that mean?
Not inverse.
I don't even have to bother checking the other one because I did not get an x here. Is that okay? Let's try another one. So if I want to decide if these are inverses, doesn't matter which one you check first, you just have to start somewhere and plug one into the other one. So let's do f composed with g first. So g is 1 over x plus 1. And I'm putting that into f. So f is 1 over whatever we plugged in minus 1. And the thing I'm plugging in is the 1 over x plus 1. Now what?
The ones cancel.
Yeah, plus 1 and minus 1 cancels. How do you divide fractions? By the reciprocal of the denominator, yep. And we get x. So is that enough to stop and say they're inverses? No, it means they probably are, but we need to check the other way. So now we need to do g of f of x. So f is the 1 over x minus 1. If I put that into g, g is 1 over whatever we put in plus 1. All right. So starting here, to divide fractions, we multiply by the reciprocal. What does that give you? X minus 1 plus 1, which is x. So, since both are x, then our two functions are inverses. Any questions there? I want you guys to try one. So we have to do the composition. F of g of x. So start on the inside. G is negative 1/3 times x minus 4. I'm putting that into f. F is 3 times whatever we plug in plus 4. And I'm plugging in negative 1/3 times x minus 4. 3 times negative 1/3, so that gives me negative x plus 4 plus 4, or negative x plus 8. So are they inverses? No. You wouldn't have to check the other way, but even if you did, you should also get that they're not inverses. So if, for instance, you had worked this one first, f was 3x plus 4, you're putting that into g. So we have negative 1/3 times 3x plus 4 minus 4. Okay? Plus 4 and minus 4 cancel, so we get a 3x. Negative 1/3 times 3x is negative x. So again, it's not x, so we would have also seen that way, that they are not inverses. All right, we are going to do 3 more slides, and then we're done for today. So, because inverses flip x and y, when you're looking at a graph, all the ordered pairs just flip the x and y. And so that means they are symmetric across the line y equals x, the identity line. So if I ask you to graph the inverse of the line y equals 3x minus 2. All right, we haven't really talked about how to find an inverse yet. We'll do that on Monday. But we could graph a line. We know how to do that. 3x minus 2. So y-intercept of negative 2. Slope of 3, so up 3 over 1. I can't draw a straight line, so I just have to put a bunch of points on here. So this is my original. If I wanted to find the inverse, we have 2 options. We could graph the identity. Y equals x has points 0, 0, 1, 1, 2, 2, 3, 3. Just our identity line. And so they should be mirror images across this line. We could also get it by taking points. This is the point 0, negative 2. So if I flip it, it becomes negative 2, 0. This is the point 1, 1. So when you flip it, it's still 1, 1. This is 2, 1, 2, 3, 4. So if I flip it, it would be 1, 2, 3, 4, 2. And so we could flip all those ordered pairs, but when you look at that, you guys see how if I folded it across that black line, those 2 lines would overlap. They're mirror images there. So this one, I just gave you a graph, not an equation, and asked you to plot the inverse. So to me, the easiest option is just to take points and look at it, and we know they should be mirror images across y equals x. So y equals x is right here, so it should look the same on both sides of that. And if you take points, this is -2, so it would stay. -1, 0, we'll go to 0, -1. This is like 0, 1, so we'll go to 1, 0. 1, 2, we'll go to 2, 1. So if we reverse all those order pairs, we see we have this mirror image. Are there questions? So, we have not finished this section. And there is a Math Excel open. We will finish the section on Monday. Technically today, you are probably able to do 1 through 13 and 18 through 24, but it's not due until Tuesday. So Monday we'll finish up and you'll have more time to